Hello everyone, this is a research paper presentation for ARTES 2020. The paper name is Program Energy Hotspot Detection and Removal, a Static Analysis Approach. My name is Mohsen Shekarisaz. I received my Bachelor in Computer Engineering from University of Isfahan and my Master from Sharif University of Technology in 2015 and 2017 respectively. I'm currently a PhD student in the School of Electrical and Computer Engineering, University of Tehran. My research interests include energy testing, energy bugs and hotspots, memory and management in non-volatile architectures, and low-power real-time embedded systems. In this presentation, at first we give an introduction about our research, then we have a discussion of the related research. As the next step, we give our system model and problem statement. Next, we explain detailed description of our approach. After that, we evaluate the effectiveness of our method by a set of experiments. And finally, we have a conclusion and give some idea as future work. Let's start with an introduction. Energy consumption is an important concern in design of embedded systems because most embedded devices in the context of CPS and IoT are battery operated. The important point is that embedded software taking the control decision has a major role on the way that the energy is consumed in the embedded systems. Various factors contribute to the energy consumption of an embedded software. In general, the system consumes some energy for computation parts. However, we can also mention two energy-hungry external resource modules like LTE, Wi-Fi, or GPS. These resources are put into active power mode for usage by registering via calling acquire statement, and also they are put into standby or sleep power mode by deregistering via calling release statement. Even if the software functionality is correct, inefficient usage of these resources in software may lead the system to consuming higher energy than the actual need, called energy issues. Two major categories for such energy issues are energy bugs and energy hotspots. An energy bug happens when a resource continues to consume energy even after the completion of the program, which is also called resource leak. However, an energy hotspot results in inefficient energy consumption by the resource during the execution of the program. For example, an energy hotspot happens when the resource is put into active power mode earlier than necessary, or it is put into sleep power mode much later than the last usage. A number of studies have been conducted to reveal energy issues through a static analysis without execution of the program, which I will talk about later in detail in related studies slide. Static analysis techniques are those that try to analyze the program statically, usually based on the control flow graph of the code. They presented frameworks to detect, validate, and repair resource leak, which is a type of energy bugs. However, some of the energy hotspots are not easily exposed to the program inspection as they need a more detailed analysis of the program to be revealed. As an example, it seems a good decision to release the resource when it is not utilized and acquire it again when needed. However, acquire and release operations impose some energy and time overheads, which have significant effects on the total energy in some scenarios. So what did we do in this research? In this research, as the first step, we introduced two new hotspots based on the mode suites of the resource, as we mentioned previously via acquire and release operations. The hotspots are based on the locations in the software code, and also we used best case execution time and worst case execution time of the specific program segment, which are called partial B set and partial W set, to define these types of hotspots. Also, we proposed an approach to investigate the program code statically without execution of the program to detect these types of energy hotspots and repair them. To this end, a static analysis approach is performed on the control flow graph of the program. Finally, we evaluated our approach and validated the energy reduction by experiments performed on an embedded system with a Wi-Fi module as the external resource. Related studies. At the software level, the previous studies are broadly categorized into testing and static analysis techniques. Some research present energy testing techniques to investigate whether or not there are energy issues. However, in spite of the static analysis, in energy testing, the program needs to be executed by test inputs to make sure about existence of energy issues. There are also several works on static analysis to find the program code energy anti-patterns like resource leak. Further, some studies try to propose approach to restructure the code without changing its behavior to reduce energy consumption, which is also called code refactoring. The focus of those research has been on revealing energy bugs, whereas finding energy hotspots through static analysis has less been investigated in previous research. Also, none of the previous works considered the two energy hotspot patterns we introduced in this paper. The relation between extreme scenarios, W set, B set, and resource power mode switching has not been considered in previous studies. In this slide and the following, we explain our system model as hardware and software models. For hardware model, we consider two hardware components, a computation unit called CPU and a single module called resource. Resource R has two modes, active mode and power saving mode. The resource is put into active mode by acquire statement. Deacquire and eacquire are delay and energy overheads to switch from power saving mode to active mode, and also the power usage of the resource in this mode is power A. Also, the resource is put into power saving mode by release statement. Derelease and e-release are delay and energy overheads to switch from active mode to power saving mode, and also power S is power usage of CPU in this mode. For CPU, we suppose that it only works in active mode, however it may switch between idle and busy states. In idle state, CPU waits for R to become active. To explain more, CPU is waiting for R to become active if use statement is called before the acquire is passed from calling acquire. In busy state, CPU only runs computational instructions. In software model, as we mentioned previously, the program P is represented by its CFG. In this research, we used a modified version of CFG with 4 types of nodes based on their statements. Acquire node, a node with a single acquire statement. Release node, a node with a single release statement. Use node, a node with one or more use statements, and also ordinary node, a node with only computation statements, to explain more with no acquire, release, or use statements. Also, we define some functions for node B small and set of nodes B capital. For example, next acquire for B small is a set of immediate acquire nodes in the path of the partial graph starting at B small node. And is similar for next release for B small and next use for B small. Also, if B capital is equal to next acquire for B small, partial W set between B small and B capital is the worst case execution time from B small to an immediate acquire statement with the most distance. Also, it is similar for partial B set between B small and B capital. Here is an example for the software model with a sample code and its corresponding sample modified CFG. As it has been specified, the sample code consists of an acquire statements, 4 computation statements, 2 release statements, and 2 use statements, and also a branch. In this example, as it has been specified in sample modified CFG, node 1 is an acquire node, nodes 2, 4, 9, and 10 are ordinary nodes, nodes 5 and 8 are use nodes, and also nodes 6 and 11 are release nodes. Problem statement. We first give our assumptions about functionally correct program P. Neither acquire nor release statements do conflict with the computational statements. Therefore, each of them can be moved up or down while only facing with the computational statements. Sequence C acquire at least one use, C release C must be preserved in the program. C represents a 0 or more computational statement, and also multiple occurrences of the sequence are possible. We define two operations on P related to resource R. Operation 1, removing a statement of release and the subsequent statement of acquire. Operation 2, moving the statement of acquire up or down while there is no conflict with computational statements. The goal is to use mentioned operations toward getting program P double prime such that the energy consumption of each individual path of P double prime remains the same as or gets better than the corresponding path of P. We present two energy hotspot patterns based on our assumptions with regards to energy-related questions. Question 1 for energy hotspot type 1 or EHT1. For any two subsequent pairs of acquire release, is it better to remove the first release and the second acquire, which have been shown by blue color, so that the two pairs will be converted to one acquire release pair? If the answer to this question is yes, then we call the program segment between the first release and the subsequent acquire a program energy hotspot type 1 or EHT1. The reason that this segment uses more energy than necessary is that the first release and the second acquire consume E acquire plus E release, which is more than the additional energy that module R consumes if it remains active between them. This scenario usually happens when the piece of code between a release and its subsequent acquire, which is executed by CPU, is relatively short. Question 2 for energy hotspot type 2. For any pair of acquire use, is acquire placed in its optimal location with respect to the first use after it? If the answer to this question is no, then we call the program segment between acquire and the subsequent use a program energy hotspot type 2 or EHT2. The reason that this segment uses more energy than necessary is twofold. If acquire is executed earlier than necessary, module R remains idle in the active mode before the time that program P reaches to use a statement, and therefore it starts wasting energy till reaching there. On the other hand, if acquire is executed later than necessary, CPU remains idle for the acquire till module R gets active, and therefore it wastes energy in the idle mode for the acquire. In this paper, we only study the later case, which CPU remains idle for the acquire. For a program, we provide the static code analysis method to detect the energy hotspots. The general procedure is presented in this algorithm called hotspot removal or HR. Given program and resource specification, the goal is to return the energy improved program considering the two energy hotspots EHT1 and EHT2. First, algorithm to remove EHT1 is called in line 1, and then the energy improved program is given to algorithm to remove EHT2. Before explaining the algorithm for removing EHT1, we first find the minimum time that the resource needs to be in sleep mode in order to eliminate the energy overheads of release and acquire operations. We call this time lower bound on sleep time or LBST. The energy of staying in active mode for LBST must be equal to the energies of releasing the resource, staying in sleep mode, and reacquiring the resource again. Based on the parameters defined in previous slides and some simple algebraic manipulation, we will have LBST as follows. The procedure for removing EHT1 is presented in this algorithm. It gets programmed along with resource specification and generates the energy improved program. The algorithm starts by constructing the modified CFG in line 1. Next, it calculates LBST based on previous slide for the resource specification in line 2. The algorithm traverses the modified CFG to collect all release nodes in line 3. Then for each release node, it traverses the modified CFG to find all next acquire nodes in line 5. Then the partial W set between the release node and its all next acquire nodes is calculated and assigned to a value in line 6. If this value is smaller than LBST, then our algorithm has detected an EHT1, and it removes the release node and its subsequent acquire nodes, allowing the resource to remain in active power mode, which has been shown in lines 8 and 9. Also, our algorithm tries to consider two special cases and try to avoid them in lines 10 to 19. The first special case is occurrence of two consecutive acquire nodes, and the second one is occurrence of resource leak in the modified control flow graph. Finally, the modified control flow graph is converted to the energy improved program, which has been shown in line 22. The procedure for removing EHT2 is presented in this algorithm. The algorithm starts by constructing the modified CFG in line 1. Then it traverses the modified CFG to collect all acquire nodes in line 2. We need to decide whether the acquire node needs to be moved backward, and if so, move it to its optimal location. If the partial B set between the acquire node and all its subsequent use nodes is less than the delay for acquiring the resource, which is the acquire, then the acquiring node needs to be moved backward. The optimal place for inserting the acquire node is where the partial B set to the next used nodes is equal to the acquire, which has been shown in line 7. Therefore, the CPU does not waste energy and time in the idle mode, and it continues processing in parallel to the acquire operation. The algorithm moves the acquire node backward, which has been shown in line 8. Finally, the modified control flow graph is converted to the energy improved program, which has been shown in line 11. Evaluation. For setup, the embedded board is an Arduino Uno with an Atmega 328P microcontroller. The external resource is a Wi-Fi module ESP8266. To measure the energy consumption, we use the USB 4716 Advantic data logger with 200,000 samples per second. To evaluate WZB set of the program segments, we used Bounty tool for Arduino Uno configuration, and also the experiments are applied for Malardon and Benchmark Suite as the embedded program. Also, we did some measurements on the Wi-Fi module to calculate LBST. For the sake of confidence, the measurements have been repeated multiple times. The average value of LBST is 3.16 seconds, and also the average of other extracted parameters have been shown. In this slide, we explain the structure of the embedded program, which comprises computations and access to resource parts. In this program, the embedded system sends the results of each n computations by a set of acquire, use, and release statements. EHT1 may happen between a release and the subsequent acquire statement, depending on the execution time of computation code between them. Also, EHT2 happens since use statement is immediately after acquire statement in this program, and enforcing processor idle time. We explain the results for a program with 6 computation parts based on previous structure. As first step, we investigate the effect of removing each release acquire pair on energy consumption for original program and its subsequent energy improved program. Removing the release acquire pair for computation 2, 3, and 4 improves the total energy since their execution times are lower than LBST. For computation 5 and 6, on the other hand, removing the release acquire pairs lead the system to consume more energy because their execution times are higher than LBST. These results validate the concept of LBST because the W sets of computation 2, 3, and 4 are lower and the B sets of computation 5 and 6 are higher than LBST, which are calculated in a static analysis phase by our approach. Also, we investigate the process of energy reduction in the HR algorithm. First, the algorithm removes the release acquire statements before and after computation 2, 3, and 4 as steps 1, 2, 3 respectively. in the procedure of EHT1, as we discussed in previous slides in main algorithms. By this approach, the total energy consumption is reduced about 21%. Next, the algorithm applies EHT2 to move back the acquire statements to the optimal points, which is in computation 1, 5, and 6 as steps 4, 5, and 6 respectively through procedure of EHT2. By this approach, the total energy consumption is reduced about 8.8%. As a result, finally, the HR algorithm reduces the total energy about 28%. Finally, we compared the power traces of the original and energy improved programs for experiments from the beginning to the end of the program execution. As shown in this figure, the system totally consumes a lower power for energy improved program, which the HR algorithm is applied to. Also, the total execution time of the original program is higher than the total execution time for energy improved one. These improvements are because of two important facts. First, the number of release acquire operation pairs are reduced, and consequently the system has not been imposed the energy and time overheads of acquire release operations based on EHT1. Second, the idle times of CPU imposed by acquire operations are eliminated, and this is based on EHT2, which decreases the active power consumed by CPU. Therefore, the total execution time and the power consumption, and as a result, the total energy consumption of the energy improved program have been decreased. Conclusion. We discussed about the importance of non-functional aspects, including energy consumption in embedded systems, and also energy hotspots in program due to inefficient use of peripheral modules. The goal of this research is to propose a code-level static analysis method for energy hotspot detection based on some relation between WSFB set of some program segments and time energy specifications of the module. The experimental results shows up to 28% of energy reduction after the hotspot removals. And also for the future work, we plan to extend the study by more patterns and analysis methods. These are references we used in this presentation. Thanks for your attention.